Welcome to today's lesson, Introduction to Linear Algebra for AI. In the world of artificial intelligence, understanding the fundamental mathematical concepts is absolutely crucial. Think of linear algebra as the bedrock upon which all advanced AI systems are built. By the end of this session, you will be able to understand why linear algebra is so critical for AI systems. You'll also learn to define and manipulate core components like vectors and matrices. We'll then explore how operations like dot products and matrix multiplication power AI, and finally, you'll see how these concepts come together to build a simple recommendation system. Let's dive in. Why does linear algebra matter so much in AI? Simply put, it's the mathematical language that AI systems use to understand and process data. Imagine trying to build a complex structure without a common language for measurements or instructions. It would be impossible. Whether it's ChatGPT processing your questions, a recommendation algorithm suggesting your next movie, or an image recognition system identifying objects, all these tasks involve converting diverse data into a numerical format. Words, preferences, pixels, they all become vectors and matrices of numbers. Without this foundational understanding, the intricate workings of every machine learning algorithm, from simple linear regression to complex neural networks, would remain a mystery. It's the core vocabulary AI speaks. Let's start with the most fundamental building block, vectors. A vector is simply an ordered list of numbers that represent something meaningful in a quantitative way. Think of it like a digital fingerprint for a piece of information. In AI, everything is vectorized. A customer's shopping preferences, for example, might be a vector where each number indicates their liking for different product categories. A word in a sentence? That's a vector capturing its contextual meaning. Just like a DNA sequence encodes genetic information, vectors encode data in a format computers can easily process, compare, and analyze, allowing AI to make sense of the world around us. While vectors represent individual pieces of data, matrices help us organize and process multiple vectors at once. Imagine a spreadsheet filled with numbers. That's essentially what a matrix is. In AI, matrices are ubiquitous. They're used to store vast amounts of training data where each row could be a data point and each column a feature. They also represent the weights in neural networks, dictating the strength of connections between artificial neurons. By structuring information in matrices, AI systems can process complex relationships and large data sets much more efficiently. It's how AI keeps its data organized and ready for computation. Now let's look at the operations that bring vectors and matrices to life in AI, dot products and matrix multiplication. The dot product is like asking, how similar are these two things? When Netflix recommends a movie, it's essentially calculating dot products between your viewing history and millions of other users to find similar tastes. Matrix multiplication, on the other hand, is the AI workhorse, especially for neural networks. Each layer in a neural network performs a matrix multiplication to transform data from one representation to another, learning complex patterns along the way. These two operations are fundamental to everything from search engines to advanced recommendation systems, enabling AI to measure relationships and transform data effectively. Let's put it all together. We can build practical AI applications like a simple recommendation system. By defining user preferences and item features as vectors, and then using dot products to calculate similarity scores, we can generate personalized suggestions, just like the code example we discussed. This simple system uses the exact same mathematical principles that power Amazon's product recommendations or Spotify's music suggestions. These concepts underpin nearly every major AI system today. Google's search ranks pages with matrix operations, Tesla's autopilot processes images as matrices, and ChatGPT represents words as vectors. The true beauty is that whether you're dealing with text, images, or sensor data, the core mathematical operations remain consistent. To test your understanding, how do vectors and matrices allow AI to find patterns in such diverse types of data?